Have you ever wondered about the world of aromatic hydrocarbons? Well, prepare yourself for an enlightening journey. This world, unbeknownst to many, is filled with chemical marvels that are as fundamental as they are captivating. Aromatic hydrocarbons, also known as arenes, form a riveting class of organic compounds that command significant interest and importance in the world of chemistry and beyond. The luminous star of this group is benzene, a ring of 6 carbon atoms, each bonded to a hydrogen atom. Benzene's molecular structure is a cyclical arrangement that alternates between single and double bonds. This alternating pattern creates an electron cloud above and below the ring, forming a delocalized, stable, and resonating system. This unusual and unique electron distribution makes aromatic hydrocarbons distinct from other organic compounds. Arenes play a predominant role in organic synthesis, functioning as basic building for a vast number of chemical reactions. They serve as starting materials for the production of many industrially significant chemicals. Furthermore, they are the core structure in many natural compounds, including several life-essential molecules like DNA, RNA, and certain amino acids. Arenes also form the fundamental structure for many drugs, dyes, plastics, and even explosives. Arenes are not just significant in organic chemistry, but they also have a central role in the realm of biochemistry, materials, science, and pharmaceuticals. Their unique characteristics and versatility make them an indispensable part of scientific research and industrial applications. These fascinating molecules, with their distinct structure and wide range of applications, truly reflect the beauty and complexity of the chemical world. So, buckle up, fellow explorers, as we delve into the enchanting world of aromatic hydrocarbons. We will be uncovering the mysteries, complexities, and wonders that these compounds have to offer. Now that we've got the basics down, we can dive into the interesting stuff. Ever thought about how aromatic hydrocarbons get their names? Well, it's all thanks to the International Union of Pure and Applied Chemistry, or IUPAC, that provides us with a standard system for naming these compounds. And what about benzene? It's a special case. Its structure cannot be represented by a single diagram. Instead, we use the concept of resonance, where multiple structures, called resonance structures, collectively represent the true structure. So, that's how we name these compounds and understand their structure. Pretty cool, right? What makes an aromatic hydrocarbon aromatic? Let's find out. Aromatic hydrocarbons, also known as arenes, are compounds that contain a ring of atoms exhibiting more stability than other geometric or connective arrangements of the same set of atoms. This unique stability, known as aromaticity, arises from a concept called resonance. It's a property that allows these hydrocarbons to act as a base, accepting protons due to the presence of delocalized pi electrons. Now, if we talk about the chemical properties of these aromatic hydrocarbons, one of the key properties is their ability to undergo electrophilic substitution. This mechanism involves an electrophile replacing a hydrogen atom in the hydrocarbon. It's a classic example of how aromatic hydrocarbons react, often resulting in compounds with new, useful properties. These properties are what make aromatic hydrocarbons so versatile and widely used. Ready to see these compounds in action? Let's dive into the reactions of aromatic hydrocarbons. Nitration, sulfonation, and halogenation are all processes that these compounds undergo. Nitration is the substitution of a hydrogen atom by a nitro group, while sulfonation involves the addition of a sulfonyl group to an organic compound. Halogenation, on the other hand, is the introduction of halogens into a molecule. Friedel-Crafts alkylation and acylation are two important reactions for aromatic hydrocarbons. Alkylation is the transfer of an alkyl group from one molecule to another, and acylation is the process of adding an acyl group to a compound. Now, let's talk about the directive influence of functional groups in monosubstituted benzene. This influence dictates the position of the incoming group in the aromatic ring. Depending on the type of group already present, the incoming group may attach at the ortho, meta, or para position. As you can see, aromatic hydrocarbons are pretty reactive. But what about the darker side of aromatic hydrocarbons? These compounds, while fascinating, also have a potential downside. They can be carcinogenic, which means they have the potential to cause cancer. Aromatic hydrocarbons are also toxic, meaning they can cause harm or even death when ingested, inhaled, or come into contact with the skin in large amounts. Now let's talk about some other properties. Ionization enthalpy refers to the energy required to remove an electron from a gaseous atom or ion. In the case of aromatic hydrocarbons, this value is relatively high due to the stability of their electron cloud. Electron gain enthalpy, on the other hand, is the energy change when a gaseous atom gains an electron. For these compounds, it's generally negative, indicating a release of energy. Electronegativity is a measure of how strongly an atom can attract a bonding pair of electrons, and valency refers to the combining capacity of an atom. In aromatic hydrocarbons, carbon atoms exhibit a valency of 4, so while they're incredibly useful, it's also important to handle them with care.